So if we take a look at the Forces 2 worksheet, question number 4. I'm going to paraphrase what it says, but it talks about Aunt Barbara sets a milk carton down that has a mass of 2 kilograms for breakfast. Her family eats breakfast, and when they are done eating, she goes to pick up the milk carton, and to her surprise, again paraphrasing, she's surprised that it accelerates upwards at 50 meters per second squared. I think they give us an upward force of some value. Part A is saying, well, why did it accelerate upwards so much? And the quick answer to that is what?
Lighter.
Yeah, it's lighter than she thought. Like, she didn't realize that people drank as much milk as she did, so they grabbed it. And if you ever done that, you go to pick up something, you think it's going to be a lot heavier than it is, and it's like, whoa, that's exactly what happened. So she applied some upwards force. What's the number on it? 20?
Yeah.
20.
Yeah.
Okay? So she applies some upward force. Much to her surprise, it accelerates upwards at 50 meters per second squared. Correct? I think that number is correct too.
Yep.
Okay. So the next question is, what's the mass of the milk carton? So it says that it's a 2 kilogram milk carton when she sets it down on the table. Now, if it was a 2 kilogram milk carton, and she were to set it, she were to pick it up, then she wouldn't have accelerated upwards as quickly as she did. Because if we were to do some quick math, well, actually, what other force is acting on this?
Gravity.
So we had a force of gravity. And if the mass of the milk carton was 2, I'm going to erase this in a second, then the value would have been 19.6. Now, if it was still at 2 kilograms, those forces are balanced or unbalanced? Unbalanced, but they're close, right? They're relatively close. So this would not have been the acceleration if that would have been the case. It would have been a much more appropriate force if it was still 2 kilograms. But it's not 2 kilograms. It's not 2 kilograms, therefore it is not 19.6, because her family drank some. So because her family drank some of it, it has an unknown mass. And that's what we're trying to figure out. The mass, however, is not 19.6. Not 19.6. So if we go through and if we take a look and we say, well, how could I determine the mass? Well, I could, if I knew the force of gravity, or if I knew the weight and the gravitational acceleration, 9.8 on Earth, I could find mass. But I don't know the weight or the force of gravity of the Aunt Barbara's now not full carbon mouth. So we can go through and we can look at Newton's second law. And Newton's second law says the sum of all my forces is equal to F net, which is equal to mass times acceleration. That's Newton's second law. Now, in Newton's second law, we have an acceleration, and an acceleration was given. That's good. I don't know the net force. I can't just say m times a is equal to F net because I don't know what the m is, so that's not really going to be super helpful. I don't know the mass. That's something I'm trying to figure out. That's what the question in part B is asking for. But net force is when we add our ups and we subtract our downs. So if I add my forces going upwards, I have 1 applied. And if I subtract my forces going downwards, I have 1, it's gravitational. We can set that equals to mass times acceleration. Now the problem with this is I don't know the mass, and I don't know the force of gravity. And the reason I don't know the force of gravity is because I don't know the mass. So that's where people kind of get stuck and you say, well, I don't know this and I don't know this, so how in the world can I do that? I have 2 equations, 2 unknowns. Well, hey, 2 equations, 2 unknowns is actually a good thing in math, right? But what we can do is we can do a substitution. And actually, Mr. Foster, in his physics classes, I don't think he ever writes f of g on the board once. The way Mr. Foster writes f of g is he calls it mg. Okay? Which is nothing, it's semantics, right? I call it the force of gravity, and he writes down mg, because how do you calculate the force of gravity? M times g, right? So it's just really a different way to do it. But the idea that I'm trying to show you is instead of, these are equal statements. So I can go through and I can take this math equation and I can do a substitution to shun, I think I spelled that right. I can do a substitution right there. So if I keep my applied force, because I know the value of that, and I'll fill that value in just a second. But instead of writing it as f of g is equal to mg, so I can, instead of saying f of g, I can say that's minus mg, right? It's a mathematical substitution. So another way to write it is m times g, and I really don't need those parentheses. I just did it to show you. And then we can say, well, that's m. Oops, I meant to put that back in blue again. And that's equal to m times a. Now, what's true? What is this the mass of?
The milk current.
This is the milk current. And what's this the mass
The
of?
milk current.
Are these the same masses?
Yeah.
Yes, they are. So, just for color coding visual purposes, those m's are the same.
So you can combine them.
I can combine like terms. So now if we go through, I know the value of applied force. It was 20. The mass, m, don't know m. G, oh, G on Earth is
9.8.
9.8. Always say positive 9.8 because G is not negative 9.8. G is 9.8. So G is 9.8, which is equal to m. Oh, don't know it. But I do know my A, and my A was 50. So if we go 20 minus m times 9.8 is equal to m times 50, you combine like terms, solve for m, and that's how you can do it. Okay. Forces to number 4. Common question that gets asked. Another kind of, it's a fairly common question, is on the back there's one about George gets in trouble for cutting down his dad's cherry tree. It's like the top one on the back. And it might be George Washington is referencing to. And it talks about an axe gets embedded in the tree. And sometimes people get hung up on the word embedded. But if I say an axe gets embedded, what am I saying happens to that axe? It gets stuck. And if it's stuck in the tree, its velocity is 0. Okay, so I'm telling you a final velocity of 0 when I'm saying that George's axe gets embedded in the tree. Just so you know that that's sometimes where people also get hung up, is on that one. Any other questions on forces 2 that you want me to kind of address before we move on? Okay. If you do, please let me know. Forces 2, the thing that worksheet was really trying to emphasize is the connection between Fab 5 and forces. And the connection between Fab 5 and forces is acceleration in Newton's second law. That's our connection piece between the two. That's what gets us from one to the next. Now, in forces 1 and in forces 2, there were definitely more forces than we needed and we cared about when we started doing our calculations. So I had some people say, do I need to do a free body diagram and figure out every single force acting on these things? And the answer is no, I don't. You can say, well, what's the point of doing all these extra forces if we don't even care about them? That's a fair question. Yet the thing is that the further on we go, like today, we're going to start needing some of those other forces that we didn't need prior. So that's why I've asked you to kind of do some of that, is to get you the practice so when we actually need them, we've already kind of introduced it, we're doing some of it already. All right, so let's talk about friction. So it's a new force. This is probably stuff you want to write down for the record. So it's a new force that we've kind of talked a little bit about, but not too much. It's the force of friction. And the force of friction, I simply write F of F. And I think the one thing we put in our kind of introductory list is it always opposes motion. It opposes motion, which means it always is working against motion. So if I'm trying to push something to the right, trying meaning not successful, if I'm trying to push something to the right, friction is pushing to the left. If I am pulling something to the left, it's moving to the left, friction's pulling to the right. It's opposing the motion. If I'm going down the highway at 55 miles per hour that way, there's a type of friction called air resistance that opposes motion and pushes this way. So it always opposes motion. It's always in the opposite direction. Now on this little sheet where we talked about friction, it was one of our highlighted ones, which means it has its own special equation. So it's one of three that have their own special equation. Force of gravity is the other one that we know of so far, but it does have its own equation. And its force of friction is equal to this weird Greek letter, and I'll talk about in a second, times our normal force. Now what this weird Greek letter is, it's the Greek letter mu, mu. M-U is how you pronounce it, mu. So coefficient of friction. So I try to match what the computers do. A lot of times people will just make the letter U, and then they just make another like leg on it. That's really all it is. I try to add the little like italicized thing, that's why I get a little bit lower tail. But that's the idea. So let me talk about that one just because it's the one that we've never heard of before. Mu represents something referred to as the coefficient of friction. It's the coefficient of friction. A coefficient is nothing more than a number. It's a number. It's a number in front of a force. So we have a force of friction is equal to some number times another force, normal force. And if we think about units, all forces are measured in what units? Newtons. So what times newtons gives me newtons? What's that?
Probably more Newton.
Well, if we did newtons times newtons, that'd be newtons squared. 1. Or nothing, right? No unit times newtons gives us newtons. That's what I'm trying to say. It's a number. It's a coefficient. There is no unit. We sometimes refer to it as unitless. It's a unitless number. Generally speaking, the coefficient of friction is a small number. It's typically less than 1. Just so you kind of have that kind of idea in your head ahead of time. Force of friction. Probably don't need to write it again, but it's force of friction. Our units are measured in newtons. So in order to calculate using its own special equation, force of friction is equal to mu, our coefficient of friction, times our normal force, which is measured in newtons. Okay? So why did we care about normal force all of this time? The answer is we really didn't. But I knew we were going to care about it once we got the friction, which is why I've been kind of throwing it in there along. So what is true about my forces acting on this table right now? What forces are acting on that table?
Gravity normal.
Right, the gravity normal. Any others? No. Okay. What's true about my what is true about the velocity of my table? Constant or changing?
Constant.
And my acceleration is?
Balance.
My acceleration is
None.
0, which means my net force is
0.
and my forces are balanced, okay? So what's true about my normal force up?
It's 98 newtons.
It could be if this was a 10 kilogram table, okay? Let's pretend that my F of G is 98 newtons.
No, that's equal.
Okay, if my force F of G is 98, then what's true about my normal force?
It's 98.
It's 98 because my forces are balanced, right? But that F of G is dependent upon the mass of the object and the gravitational acceleration that they are, which we're on Earth unless I tell you otherwise. So let's just pretend that that's a 98 Newton table. Okay? Most of the time, and we said this before, most of the time my normal force and my gravitational forces are the same. Most of the time. Not all the time, and yesterday we did one problem, and it's kind of that idea, is if I go and I lift up on this table, and I lift up, but I'm not strong enough to lift up, is my normal force still equal to my weight? The answer is no. My forces are still balanced, but my two forces up minus my one down have to add up to that zero. Okay. Most of the time, our normal force is the same as our gravitational force, but it's not always that point. All right, so now friction. When we talk about friction, there's three types of friction that we often refer to. We're going to talk about one today right now for a little bit, and then we won't talk about it probably ever again, and it's called rolling friction. And when an object rolls across the surface of another, like my bowling ball, or the tires on your car, that's called rolling friction. Rolling friction is not something we are going to really address and deal with because it would fall in a rotational motion unit, which I haven't done a rotational motion unit in a couple years, and I don't plan to. But the idea of rotational friction is important. And when we think about objects stopping, rotational friction is better than sliding friction. So the friction we're going to talk about is sliding. There's two types of sliding friction. That's what we're going to spend our time talking about in this class, besides right now. Sliding friction is not as effective at stopping vehicles as rolling friction is. So why do we care about stopping in vehicles? Well, it's kind of an important part of driving. Stopping, going, steering, kind of big deals. Most of the time, we don't really care about, we aren't that concerned about sliding versus rolling friction. But we're getting to that time of year when rolling versus sliding friction is more of a thing. We got a little rain today. When we get some rain, it changes how slippery things are. Changes our coefficient of friction. But generally, a wet pavement isn't like terribly different than dry pavement, assuming your tires are decent tires. Like they have some traction on it. Generally, it's not that big a deal. But what happens once we get a little bit of snow or we get some ice and we step on our brakes and we want to stop? We want to stop, and that's important. So I mentioned that rolling friction is better at stopping vehicles than sliding friction. If you lock up your brakes, you step on your brake as hard as you can, and you don't have anti-lock brakes. You step on your brakes as hard as you can, you lock up your tires, you just slide forward. And you keep sliding, and you are slowing down a little bit, not as much as you want to, and not as much as you should be probably. And depending upon the distance you are, you might hit something or someone. So sliding friction is not great when we're talking about like ice and snow, but rolling friction is much, much, much better. So the idea is if your tires keep rolling, we can stop our car much faster than if we lock up our tires and slide. So that's the whole purpose of anti-lock brakes. So I'm assuming they still teach it in driver's ed, but if you don't have anti-lock brakes and you feel yourself start to slide, what are you supposed to do with your brake pedal? Pump it. Pump your brakes as fast as you can. It really seems counterintuitive to take your foot off the brake when you're worried about slamming into something, but it works. However, I'm going to say probably most vehicles that are being driven by people in this room, I'm not saying all, but most probably have an anti-lock braking system on their cars, because that's become is more common. I'm not saying they all have, but it's much more common. Now what an anti-lock braking system does is it's just, there's a computer that measures your wheel speeds, and when it senses that they start to slip, they start to pulse your brakes for you. And you say, well, how do I know? Well, generally speaking, when you turn on your car, there should be a little indicator light probably that says like ABS on it. But the other way you know is if you ever step on your brakes and you feel your brake pedal pulse or vibrate, that's your anti-lock braking system pumping your brakes for you. And if you have anti-lock brakes, step on that brake, hold that brake, and cross your fingers and hope you stopped in time. But that's really the best you can do once that is built. That's rolling friction. We're not going to deal with rolling friction more. That was just my public safety announcement about anti-lock brakes. And you don't have them, pump your brakes. If you do, press and hold. I had a student a couple years ago who swore that they could pump their brakes faster than their anti-lock brake system. I knew I wasn't going to win that conversation, so I just smiled and nodded. I'm like, oh, okay. And then I went on with my life because I knew I wasn't going to convince him otherwise. So you might be good, but not that good. Anyways, so that's rolling friction. I'm done talking about rolling friction. We're going to talk about two objects that slide next to one another. Okay? Now, when we talk about two objects that slide next to each other, there's two types of sliding, or two types of motion, I guess, we talk about when we talk about sliding things. We are going to deal with something called static friction. And I'm going to leave a couple lines between static friction and this next one, just for the record, if I were in a notebook. Static friction versus kinetic friction. Okay, so those are my two types of friction that we are going to deal with in this class. The nice thing about the two types of friction, they use the exact same equation. There's only slight differences is they have different coefficients. So what that coefficient of friction is it's a number, and it's based upon what two objects are sliding next to each other. Okay, and that coefficient of friction changes based upon the materials. So if I rub my hand across the wood table, that has some coefficient of friction. If I rub my hand against my two hands, that's a different coefficient of friction. If I rub my hand against the whiteboard, that's a different coefficient of friction. Okay, two different objects. If I change and I put hand sanitizer, I got a different coefficient. Okay, good. So when we talk about coefficient of friction, I talk about my two hands moving against each other, or my table against the floor. That's the example I'm going to use here in a moment. They have different coefficients of friction, whether it's static friction or kinetic friction. We still use the same equation. This value is just different. That's really the only thing. So let's talk about the difference between static friction and kinetic friction. If something is static, or has static friction, it is not moving. So when we have static friction, it is not moving. However, if something has kinetic friction, it is moving. Can something have friction? It says static, it can. But can something have friction and not be moving? Yes. If I grab a desk and I pull on the desk, and if it doesn't move, but I did pull, what was holding it back? Friction, right? Because it wasn't moving, it's static friction. Okay, that's the difference between static friction and kinetic friction. Now, once it is moving, then it's kinetic friction. Slight variations in the formulas I'll write down in a moment. Static friction versus kinetic friction. When we talk about static friction, it's not moving. It's and this one gets a little tricky, so I'm going to do my best to describe it and explain it the best that I possibly can. When we calculate force, static friction, I said formula is the exact same. We sometimes get a little fancy. Instead of saying force of friction, it's force of friction, comma, S for static is equal to mu of S for static coefficient of friction times our normal force. So it's really the same. It's really the same equation. We're just calling it static friction versus coefficient of friction. So the static coefficient of friction. So that is there's a number, and there is a number that we can calculate. Our formula for kinetic friction looks very similar, and in fact, most of the time I don't even differentiate between the two, I just call it F of F. But we could say F of K, force of friction comma K, is equal to mu of K times our normal force. Again, the only difference between static friction and kinetic friction in terms of calculations is we have to use the appropriate coefficient. If it's moving, we use the kinetic. If it's not, we use the static. That's the difference in our calculation. Now what happens is it varies a little bit once we start addressing the numbers. So let's quickly talk some numbers. So I have some table. Pretend this is my table. And we have a table in the front of the room, and we said that it has some force of gravity and it has some normal force associated with it. Okay, it's some numbers. I don't care what they are, 50, 1,000, 10, 2, whatever. In that situation, what's true about my normal force and my gravitational force? They're equal. Okay, good. So they're equal. Now, if we were to go through and because this table, if I try to slide this table on the floor, there's some friction against, okay? So because it's not moving, there's some static coefficient of friction, and once I get it moving, there's going to be a different coefficient of kinetic friction. But if I were to go through and I calculated, and I'm completely making this number up, if I were to calculate that my static force of friction was 20, I take my normal force, multiply it by my coefficient of static friction, some made-up number. I'm making up a new made-up number. My number's 20. You with me so far?
Yeah.
There's a force friction of 20 if it's not moving. Now, if I start to pull on this table to the right, why doesn't it move?
You're applying the force.
But what's opposing me?
The friction.
Friction. Good. Okay, so let's talk for a moment about that. Friction. Agreed. 100% friction is going to be pulling against me. Is it moving? No, it's not. Good. So it's static force friction. Here's my handy dandy little scale. And if I pull at 10 newtons, pulling at 10 newtons, but my table's not moving, right? What's true about my forces? Balanced or unbalanced?
Unbalanced.
Wait, what?
You gotta really pull.
Well, what happens if my forces are unbalanced then? My velocity
Changes.
changes. And then it means it would accelerate or not accelerate.
Accelerate.
Well, it's not accelerating
It's not
though, right?
accelerating, no,
Okay,
but
so if I pull at 10,
Yeah.
10. Okay, let's write some numbers on the board. So if I pull at 10, I pull 10 newtons that way. Force of friction is going which way?
To the left.
To the left. How big?
And 20 according to your scale.
Right, no, according to my scale I was pulling.
No, I mean like your diagram.
Oh, okay. So let's ignore this for a moment.
I don't know.
Let's ignore this for a moment. Was my velocity constant or changing when I pulled at 10?
Constant.
It was constant, so it means my acceleration is
More than.
balanced. My acceleration was 0, my forces were balanced, my velocity was constant, and my forces need to be balanced. So ignore that number that I told you before, 20, just for a second. Ignore that for a second. If I pull 10 to the right, but my velocity doesn't change, what must be my force to the left?
More than
10,
10.
I agree, 100%. This is equal to 10 newtons. But if we calculate it as 20. Okay? Now this is what I'm going to say, this is why I'm saying this. When we talk about the static coefficient of friction and the static force of friction, it's a range, it's a value. It's from 0 to the maximum calculated value. So my calculated static coefficient of friction is 20, but it's a maximum value. Because let's just pretend for a second that that was a fixed number. So that means if I pull like this at 10, and static friction pulls that way at 20, are those balanced or unbalanced?
Unbalanced.
Those are unbalanced. So that, which direction were they, would that be unbalanced then, in our hypothetical situation? That way, right? If I pull this way at 10 and friction pull that way at 20, my forces are unbalanced that way, which means my object's going to accelerate that way. And does that actually happen? Do I pull a little bit this way and then all of a sudden, they go flying that way? No, right? That's why I'm trying to emphasize it's a range. It's a 0 to maximum value. Okay? So if this was 10 and it doesn't move, I didn't exceed that maximum value, my force of friction is going to be 10. If I pull a little bit harder and this becomes a 19, did I overcome the maximum value?
No.
So what's true about my forces, balanced or unbalanced? They got to be balanced, so that's also going to be 19. I go a little bit harder, I'm still at 20, my forces are still going to be balanced, still no change in velocity though. You okay with that? Okay, now once I pull hard enough to say get 21 newtons, what is true about the maximum value? It can only be 20 newtons, 21, I think I said 21, 21 newtons.
Unbalanced.
The max is unbalanced. What's going to happen to my object's velocity?
It's gonna go down, up.
It's going to change. It's going to accelerate. In which direction is it going to accelerate?
That way.
Towards the unbalanced force. Now, if it starts to accelerate, what does that mean? Is it static friction or is it now kinetic friction? It's now kinetic friction. Okay? Now, the thing about kinetic friction, it is a fixed value. It's a fixed value. That means once it starts to move, that's the number. If it's moving at 1 mile per hour, that's the number. If it's moving at 20 miles per hour, it's still that fixed number. Okay? That's the big thing about frictions. We have to overcome the static force of friction. Once we overcome that maximum value, we get an acceleration, which then gets the thing to start moving, and it switches to kinetic. And that's a fixed value. Then we can look at a different free body diagram, and then maybe this becomes 10, and this becomes 21, and then we have a different acceleration. Now I'm going to make a general statement about static versus kinetic friction. Generally speaking, static friction is higher, bigger than kinetic friction. Generally speaking, it's harder to get something to start to slide than it is to keep it sliding. Think about a heavy box on the floor. You push, you kind of give it a shove, and once you get it to start to move, it's easier to keep it moving or to keep it sliding. Okay? So that's a general statement. It's not an always statement. No, I think it's a good statement. Most of the time, at least, maybe I should keep it as the most of the time. Your static friction is going to be bigger. You have to give it an initial shove to get it to start to move. And once it starts moving, it's going to be easier than if it's stationary. All right, I got a little bit of time. With that time, we'll be good. This is not a homework sheet yet. It will be, actually, you need one. It will be at some point, don't worry about it. We'll talk about that tomorrow. We're going to do one, maybe two of these problems together in class. So once you get this is free body diagrams. It just has some friction examples on it. And when we start talking about friction, when we start talking about friction, we can start doing some free body diagrams, because that's why I had you doing all those free body diagrams with normal force, even though we really didn't care about normal force yet. So if we take a look at this top one, in interest of time, I'm not going to do anything with. Well, that should look familiar. because it's exactly off of another worksheet that we did before.
Free body diagrams.
We're not gonna do that first row, okay? But what it is just looking at forces once again, balance versus unbalanced, bigger versus smaller, how much bigger are they, that kind of thing. That had nothing to do with friction. So now we're gonna talk about the friction ones, and we're gonna look at the second one. This second one is something similar that we've already done before. This doesn't have anything to do with the coefficient of friction. It's really just looking at forces to the right, forces to the left. And now we're talking about friction, and we can kind of use it. It's a good kind of stepping stone to get us going in the right direction. So it says a rightward force is applied to a 6 kilogram object. I like to put 6 kilograms in the middle. They put it right here, but ooh, you can't see that. 6 kilograms. Across a rough surface is just like a generic way that they can say there's going to be friction. The smoother the surface, the less friction. Like ice, like a hockey rink isn't frictionless, but it's going to be a little bit of friction compared to like a gravel road. Okay, so that's what rough surface that gives me that. Oh, hey, constant velocity. What does constant velocity tell us?
Balance.
It's not moving.
That no, it doesn't mean it's not moving. It means that it's not accelerating. And your forces, I heard balance, and your F net's going to be 0. Okay? Constant velocity is what tells me that my acceleration is 0. The object encounters a 15 Newton force of friction. Use the diagram to determine the gravitational force. Okay. So, a typical question like this would probably be everything the same, but instead of find all these things, use the diagram to determine the gravitational force, normal force, net force, and applied force. The question would be, what's the applied force? That's a typical question that would actually come out of these if we weren't just doing free body diagrams. So let's start with our easy, what I consider to be easy forces. And if we were to go through and we say, hey, I need to calculate the force of gravity is equal to m times our gravitational acceleration. And on Earth, that's going to be 6 times 9.8. And our F of G then is going to be 58.8 newtons. 58.8 newtons. Now, F net is 0 tells me my forces are balanced or unbalanced.
Balance.
What about in the x direction? Are they balanced or unbalanced?
Balance.
And in the y direction? They're also balanced. Okay, so if my forces in the y direction are balanced, and I only have one up and I only have one down, what's true about those two
They're the
values?
same.
They're going to be the same. So what's my normal force in this situation?
58.8.
Very good, 58.8 newtons. And what's true about my forces in the y direction, or in the x direction?
Also balance.
All is going to be balanced. And if I only have one to the right and I only have one to the left, what's true about their two values?
They're the same.
They're going to be the same. Now where that comes from, just for the record, is the sum of all my forces is equal to F net, which is equal to mass times acceleration. If our acceleration is 0, my F net is 0. When I add my forces to the right, and I subtract my forces to the left, they have to add up to 0. And a little, oh, that's a minus, I have to add it to the other side, a little bit of lazy math, and I make that minus sign an equal sign, and ta-da, look at that, they equal 1. Okay. Let me get started on this next one. It's a very similar question. A rightward force is applied to a 10 kilogram object, and it's moved across a rough surface at a constant velocity, which means my acceleration is 0 and my F net, oops, you couldn't see that, sorry. And constant velocity, acceleration is 0, my net force is 0. The coefficient of friction, blah, 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 is 0.2. The coefficient of friction, blah, 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 is 0.2. What that's telling me is mu is equal to 0.2. That's just where this person who wrote this worksheet, wasn't me, likes to put it. It's fine, whatever. Okay, there's some coefficient of friction. Now what's true about my forces in the x direction?
Equal.
They're equal and they're balanced. What is true about my forces in the y direction?
Also balance.
They're also balanced, right? So F of G is equal to m times G. F of G is equal to 10 times 9.8. This is 98 newtons. What's true about my normal force? 98 newtons, because in the y direction my forces are balanced. My forces in the x direction are also balanced. I just don't know what that number is yet. Force of friction has its own special equation. And if we know enough information, we can use its special equation. We can always use Newton's second law. But force of friction is equal to our coefficient of friction, which is given in the problem as mu of 0.2. We just determined or calculated our coefficient of, our normal force to be 98, which if we take mu, 0.2, times 98, we get a value of 19.6 newtons. This is 19.6 newtons. And if my net force is 0, what's true about these two forces? They are balanced, which means if there's only one to the right and only one to the left,
They're the same.
they are the same. Okay? That's a good stopping point. We're going to keep building on this with friction. Have a good day.